In this video, we're going to talk about some of the theoretical foundations of creating programs that solve problems intelligently. We will be exploring the concept of agents and the environments in which they work. So an agent is an abstraction, and it is an entity that interacts with an environment. It interacts with it by perceiving things in the environment and performing actions that manipulate the environment. So it's able to perceive by some sensors that it may have, and it's able to perform actions with actuators. The agent should be rational, and we'll talk about that in a minute, and its performance is evaluated in some objective way by something called a performance measure. So in terms of defining an agent's intelligence, human intelligence may not be a very good benchmark. Humans are notorious for acting against their own interests. There's going to be plenty of examples of that come election day this year. And so when determining whether or not an agent is intelligent, rather than basing it off of what humans would do, we'll have this notion of rationality. And rationality is based on whether an action performed maximizes some expected outcome. Importantly, the agent is going to have to operate under some amount of uncertainty in most cases. Certainly all situations that are difficult to solve and usually worth solving have some amount of uncertainty in them. So, given that there's some uncertainty, the agent is still going to need to be able to choose what seem to be, at least, rational actions, not necessarily knowing what the outcomes are going to be. So, the important point is that rational agents do the right thing under this uncertainty. Now, the right thing is going to differ depending on what the problem is to be solved, but it should be something that is maximizing some metric, some performance measure. It is getting it closer to solving some problem or optimizing some value. So, given some set of actions, the agent should choose one that maximizes this metric. This choice will be based off what it's perceived presently and in the past, as well as any knowledge that it has been given at the start of the problem. Now, in terms of rationality, there could be some limitations, such as being able to compute all possible outcomes. And given that, you could still choose a rational action given the information that you are able to compute. And we're not saying that the agent needs to know everything about the environment or everything that is to come. Just that given what it knows, it's able to choose the best action that maximizes that expected return. And this might also involve the agent doing things that may not immediately seem to be rational, but could be if it involves exploring the environment, gathering information in some way so that it's able to make rational decisions in the future. So as an example, we're going to use a very simple environment, this vacuum cleaner world. The vacuum cleaner world is made up of some number of rooms. In the diagram here, there's just 2 rooms, and each room can either be clean or dirty. The agent is able to perceive which room that it's in and whether or not there is dirt in that room. The actions it's able to take are to move into one of the different rooms, and then it's able to suck up dirt. So here is a state space of the vacuum world with only 2 rooms, and we can see the transitions from one room to the next. L and R are moving left or right, and S is sucking up dirt. So you can see that if it's in the leftmost room and it sucks up dirt, then it ends up in a state where there's no dirt in the leftmost room. So this performance measure needs to be some objective means to determine whether or not the agent is acting in a rational measure. That is, it needs to serve as some way to measure the quality of the agent's behavior. And this measure should be based off more the state of the environment, not so much the state of the agent. Though this distinction can be a little bit fuzzy, but we don't want the agent to be able to kind of make it appear that it's doing a great job when really it's not, based off some metric that it keeps internally. So as an example of this distinction, if we were to come up with a performance measure for a vacuum cleaner agent, a naive one might be, well, the amount of dirt it cleans could serve as a good way of indicating whether this vacuum bot is doing a good job. But this is actually a terrible idea because the agent could simply suck up some dirt and then drop it back onto the ground and suck it up again and just keep performing this while all the other rooms in the environment remain dirty. It's sucking up a lot of dirt, but that's only because it's depositing that same dirt. So instead, we could measure the number of rooms that are presently clean in the environment, the amount of time it took to do that, and maybe some other metrics that might be relevant to the particular problem, such as power consumed or noise generated. But importantly, the notion of how much dirt it cleans is more of a representation that the agent might keep as part of its internal state rather than something that represents the environment itself. So taking these ideas of an environment, an agent with its actuators and sensors, and a performance measure together, let's look at an example of an automated taxi driver. So the performance measure here would hopefully be that the agent is driving safely and following the laws. And note that the laws are objective in that they are defined outside of the agent. And so we could know whether laws were abided by. And we could measure safety in terms of, nobody got hurt. Now you could argue, well, safety, that's a little bit fuzzy too, because maybe the agent would be safest if it just never pulled out of the garage. So we wouldn't want safety alone to be the only performance measure, though it should certainly be one. We also want to see what kind of profits the agent would be able to generate, and certainly wouldn't be able to get any if it just stayed in the garage. The environment, of course, would be the road, other cars, pedestrians. These are all things I'll have to take into account. The weather, maybe the road is icy. Its actuators, steering, being able to signal to other agents, which include other drivers as well as the pedestrians, and accelerating, of course. And then its sensors would include, of course, things that you've seen on a self-driving car, cameras, GPS, and other things like LiDAR and the like. And so all these things taken together allow us to measure an agent's performance, the agent having been defined in terms of what it can perceive and what it can do in a particular environment, with some way of determining whether it's doing those things well. Finally, we can group environments into general categories. And this can be helpful because some categories require different sorts of solutions than others. So the first category we have is observability, and this is determining how much of the environment is able to be perceived at a particular point. So a fully observable environment would be like a lot of board games. You can see all the pieces on the board. This doesn't include some like Battleship, of course, but for many board games, you can see all the pieces on the board. You have full observability of it. Partial observability could be something like many card games where you're not showing each other's hand. You see your hand, you don't see the hands of others. Determinism is whether or not we can predict what a successor state is going to be given an action. So if you recall, the transition model states that given a state and an action, we generate some successor state. Well, if the environment is not deterministic, if it's stochastic, that means we don't know for sure what that successor state is going to be. It could be from some set of successor states, and we need to account for all those possibilities. And we'll talk more about that in another video. Continuity is whether the consequences of particular actions are relevant across multiple tasks that need to be performed. And this is also a little bit blurry. A good example of it is an agent that plays chess. So we could potentially think of a chess match as being episodic in that once the match is over, it really has no relevance to another match that might be played. However, if the match were to take place in a tournament, then losing a match would then disqualify one from the tournament, and then you wouldn't be able to move forward in winning the thing as a whole. So it kind of depends on how much you zoom into the problem sometimes, whether it's episodic or sequential. Easier examples would be like a robot in a factory that's just sorting parts. Given some parts, it sorts whatever into bins and then it gets the next set of parts and so on. That would very much be episodic. Though you could argue, well, what if it drops some parts and then that impacts how it's able to sort the next batch? Again, it's a little fuzzy. Transitivity determines whether the environment continues to change while the agent is deliberating, while it's trying to choose what action to take next. So in a static environment, everything is just kind of on pause. Nothing changes. The agent is able to take as much time as it wants to determine what action to make, whereas in a dynamic environment, everything is changing. So a self-driving car, of course, the environment doesn't just stop because the agent's trying to figure out what it should do next. Though many types of board games are static, but there are many games where time is relevant, like tournament chess, and so that clock does add a certain amount of dynamism to it, and it's often referred to as being semi-dynamic. Whenever time is the component that changes, nothing else about the environment's changing but time, and time is relevant, it's said to be semi-dynamic, so it's kind of in between the two. Precision is how we can break up states. So in the real world, it's of course continuous, but in board games and there are many situations where we can break up things into discrete blocks, and so we would say that environment type falls in that category. Now, in a continuous environment, we can often discretize certain components of it, round values, so we can bin them in certain ways, and then the environment could be said to be made discrete. We also may have to take into account that there could be other agents involved in the environment. So in a single agent environment, the agent in question is the only actor in that environment. That's not to say that there isn't any sort of adversity. It still may have to overcome some challenge, but there aren't other actors that are trying to thwart it. And similarly, there's no other actors that are trying to help it. So other actors can be cooperative, and that would still be considered a multi-agent environment, but a lot of the time they're competitive and they're trying to thwart the agent. They're trying to prevent it from achieving some goal, especially in a zero-sum game where there can only be one winner. And then finally, there's this notion of knowledge. That is, does the agent even understand how the environment works? And this might seem kind of ridiculous. Like, how could the agent even begin to solve the problem if it doesn't know how the environment works? Well, this sort of problem is addressed in reinforcement learning, where the agent just has to try like lots of random actions and sort of figure out what the consequences are across many different trials before it sort of sees how the environment functions. Okay, so those are the basics of the agent model, the environments that an agent may need to work in, and ways of determining whether the agent is doing what it should be, if it's performing rationally, that is, doing the right thing under uncertainty. In the next video, we'll talk about what to do if we don't have certain information, that is observability or determinism, how we can still make rational actions.